the next topic of derivative, which is derivative of implicit function. First we know about the implicit function. What is implicit function? You know about regular function, which is y is equals to f of x and x is equals to g of y. After differentiate, you find the derivative of y with respect to x, derivative of x with respect to y. Here we find dy by dx. Here we find dx by dy. These whole functions are in the explicit form. But today we learn about the explicit form or explicit functions. If y is equals to f of x and x is equals to g of y are said to be explicit form, but if an equation in x and y is given and x is not an explicit function of y and y is not an explicit of x, then either of the variable is an implicit function of another. It means that if the given function are in x and y together, then their form is a implicit functions. If we know about the derivative of implicit function, differentiate both sides of the equation with respect to x, which with respect to independent variable, treating y as differentiable function of x, and collect the terms of containing dy by dx on one side of the equation and solve for dy by dx. Some examples are given below, which is in the form of explicit functions. Question number first, find dy by dx. If the function is x raised to the power 5 plus xy cube plus x square y plus y raised to the power 4 is equals to 4. The given function is in implicit form. When the function was in form of explicit, then function y is equals to f of x. After differentiating with respect to x, we get dy by dx is equals to f dash of x. But here the function is in the form of implicit. If we have to find dy by dx, then first differentiate with respect to x given function. After differentiating, we can take a separate derivative of every terms. Hence we can write derivative of x raised to the power 5 plus derivative of x into y cube plus derivative of x square into y plus derivative of y raised to the power 4 is equals to derivative of 4. We know that the derivative of x raised to the power n and the derivative of x raised to the power n is n into x raised to the power n minus 1. Hence we can write it derivative of x raised to the power 5 is 5 into x raised to the power 5 minus 1 is 4, plus we can apply here u into v. Derivative of u into v is u into dv by dx plus v into du by dx. Hence we can write it x into derivative with respect to x of y cube plus y cube into derivative of x. After that, second term, derivative of x square y is x square into derivative of y plus y into derivative of x square plus derivative of y raised to the power 4 is 4y cube into dy by dx is equals to derivative of constant function is 0. Here we take y raised to the power 5 with respect to x, 4 into y cube. Y is considerable function. Again we can take a derivative of y, which is dy by dx with respect to x. After that we can write 5 into x raised to the power 4 as it is plus x into derivative of y cube is 3y square into again derivative of y dy by dx plus y cube as it is and the derivative of x is 1 plus x square as it is into dy by dx plus y as it is derivative of x square is 2x plus 4y cube into dy upon dx is equals to 0. After that we can write here 5 into x raised to the power 4 plus y cube into 1 is y cube plus 2 in y into 2x is 2xy plus 3 x y square into dy by dx. Second terms of dy by dx is plus x square into dy by dx plus third term of dy by dx is 4y cube into dy by dx is equals to 0. After that, we can take dy by dx common from all these three terms. If we shift this term, whole terms in the right side, then we can write 3xy square plus x square plus 4y cube into dy by dx. These terms are positive. If we shift right side, then we can write minus 5x raised to the power 4 plus y cube plus 2xy. If we have to find the value of dy by dx, then we can shift this whole term in right side. This term are multiple to dy by dx. If we shift right side, then it divide 5x raised to the power 4 plus y cube plus 2xy. Hence we can write dy upon dx is equals to minus 5x raised to the power 4 plus y cube plus 2xy upon 3xy square plus x square plus 4y cube, which is a required derivative of y dy by dx when y is equals to, when the function x raised to the power 5 plus xy cube plus x square y plus y raised to the power 4 is equals to 4. Write down. Again, example number 2, y cube plus cos of xy is equals to x square minus sin of x plus y is an implicit function, and here we have to find the dy by dx. dy by dx means derivative of y with respect to x. If we differentiate a given function with respect to x, then we can write it separate the derivative of y cube with respect to x. Again, separate the derivative of cos of xy is equals to derivative of x square minus derivative of sin of x plus y. Here the derivative of y cube is 3y square, and we take again a derivative of y, which is dy by dx, plus derivative of cos of xy. Derivative of cos is minus sin, hence we can write minus sin of xy, and we take again a derivative of x into y is equals to derivative of x square with respect to x is again 2x minus derivative of sin is cos of x plus y, and we take again a derivative of x plus y. After that, we can write it 3y square into dy by dx as it is minus sin of xy into, here we apply the rules of u into v, which we can write x into dy by dx plus y into derivative of x is equals to 2x as it is minus cos of x plus y, and the derivative of x plus y, which is derivative of x is 1 and derivative of y is dy by dx. After simplifying, we can write it 3y square into dy by dx minus sin of xy into x minus x sin of xy into dy by dx plus minus minus y into sin of xy, and the derivative of x is 1 is equals to 2x minus cos of x plus y into 1 cos of x plus y. This term minus plus minus, we can write it minus cos of x plus y into dy by dx. We have to find dy by dx. Whole terms of dy by dx we take left side, and remaining terms we shift on the right side. We can write it 3y square dy upon dx minus x sin of xy into dy by dx. This term minus cos of x plus y dy by dx is negative. If we take the left side, then we can write plus cos of x plus y into dy by dx is equals to this term 2x minus cos of x plus y as it is, and minus y sin of xy. If we shift right side, then we can write plus y sin of x into y. If we take dy by dx common from whole this term, we can write 3y square minus x sin of xy plus cos of x plus y into dy by dx is equals to 2x minus cos of x plus y plus y sin of x into y. It is clear that we have to find the value of dy by dx. Remaining whole terms without dy by dx we shift right side. These terms are multiple to dy by dx. We can write here dy by dx is equals to 2x minus cos of x plus y plus sin of x plus y upon 3y square minus x sin of xy plus cos of x plus y, which is the required derivative of y, is dy upon dx. Next one, example number 3 is x square plus e to the power xy is equals to y square plus log of xy. Here we have to find again dy by dx. If we find the dy by dx, then first we differentiate whole function with respect to x. After differentiating, we can write derivative of x square plus again the derivative of e to the power xy is equals to derivative of y square plus a derivative of log of x plus y. We know that the derivative of x square is 2x plus derivative of e to the power xy is e to the power xy into again the derivative of xy is equals to derivative of y square is 2y into dy by dx plus derivative of log of x plus y is 1 upon x plus y, and we take again the derivative of x plus y. Again we can write 2x as it is plus e to the power xy, and we write the derivative of x into y is x into dy by dx plus y into derivative of x is equals to 2y into dy by dx plus the 1 upon x plus y, derivative of x is 1 and the derivative of y is dy upon dx. Again we can write it 2x plus e to the power xy into x into dy by dx plus y into derivative of x is 1 is equals to 2y into dy by dx plus 1 into 1 upon x plus y is 1 upon x plus y plus 1 upon x plus y into dy by dx. Now if we multiply this term e to the power xy in bracket, then we can write 2x plus x into e to the power xy into dy upon dx plus y into e to the power xy is equals to 2y into dy by dx plus 1 upon x plus y plus 1 upon x plus y into dy by dx. After that we can write, we take a whole terms of dy by dx on left side and remaining terms are right side. Hence we can write it x into e to the power xy into dy by dx. This term are positive. Here if we take right side, then we can write minus 2y into dy by dx. This term are again positive. We can write it minus 1 upon x plus y into dy by dx is equals to 1 upon x plus y as it is. This 2x, we can write it minus 2x. This y into e to the power xy can write minus y into e to the power xy. If we take dy by dx common whole terms, then we can write x into e to the power xy minus 2y minus 1 upon x plus y into dy upon dx is equals to 1 upon x plus y minus 2x minus y into e to the power xy. If we multiply each term x plus y, then we can write x into e to the power xy into x plus y minus 2y into x plus y minus 1 upon dy upon x plus y into dy by dx is equals to 1 minus 2x into x plus y minus y into e to the power xy into x plus y upon x plus y. Here x plus y cancel. We can write dy upon dx is equals to this term 1 minus 2x into x plus y minus y into e to the power xy into x plus y upon this term, as in form of multiple we can write in denominator x into e to the power xy into x plus y minus 2y into x plus y minus 1, which is the required derivative of y, dy upon dx. Question number 2 is x raised to the power m into y raised to the power n is equals to x plus y whole raised to the power m plus 1. If we find the value of dy by dx, then we prove dy by dx is equals to y by x. First we write given function, given that whole terms is x raised to the power m into y raised to the power n is equals to x plus y whole raised to the power m plus n. Here we have to prove that dy by dx is equals to y by x. The given function is in complicated form. Also, this function is a implicit function. First we take log on both sides. If we take log both sides, then we can write log of x raised to the power m y raised to the power n is equals to log of x plus y whole raised to the power m plus n. We know rules about the log of m into n is log of m plus log of n. This term we can write separate, x raised to log of x raised to the power m plus log of y raised to the power n is equals to log of x plus y whole raised to the power m plus 1. Also we know that log of m raised to the power n is n log of n. Similarly we can write here for each term, this term we can write m log x plus this term also we can write n log y is equals to m plus n into log of x plus y. Now if we differentiate with respect to x, then we can write the derivative of m log m is constant function and the derivative of log x is 1 by x. Again n is constant function, derivative of log y is 1 by y, and we can write again dy by dx. Here m plus n as it is, derivative of log of x plus y is 1 upon x plus y, and we take again the derivative of x plus y. After that we can write in this term m upon x plus n upon y dy by dx is equals to m plus n upon x plus y into dy by dx. We take a derivative of dy x, derivative of x with respect to x is 1 plus dy by dx. After that we can write it m by x plus n by y dy by dx is equals to m plus n upon x plus y dy by dx into 1 is m plus n upon x plus y into dy by dx. Sorry, here m plus n upon x plus y into 1 is m plus n upon x plus y plus m plus n upon x plus y into dy by dx. If we take all dy by dx term in left side and the remaining terms are right side, then we can write n upon y into dy by dx. This term positive become minus m plus n upon x plus y into dy by dx is equals to m plus n upon x plus y minus m by x. Now we can take dy by dx common both terms and we can write n upon y minus m plus n upon x plus y into dy upon dx is equals to m plus n upon x plus y minus m upon x. If we take cross product of both terms, we can write it n in bracket x plus y minus y in bracket m plus n upon y into x plus y into dy by dx is equals to x in bracket m plus n minus m in bracket x plus y upon x in bracket x plus y. Here x plus y cancel. If we multiply n into bracket x plus y, we can write nx plus ny. Again y into m plus 1 is minus ny into upon y into dy by dx. Similarly, we can write it m into x is mx plus nx minus mx minus my upon x. Here plus n plus y minus n plus y cancel. Again here plus m plus x minus m plus x cancel. We can write it nx minus my upon y into dy by dx is equals to nx minus my upon x. Here nx minus my, nx minus my are similar terms are cancelled. We can write it 1 by y dy upon dx is equals to 1 by x. If we shift this y on the right side, then we can write dy upon dx is y by x, which is a required proof of the given function dy by dx is equals to y by x, hence proved. Next example, which is question number 3, is if the sign of px raised to the power m minus qy raised to the power n upon px raised to the power m plus qy raised to the power m is equal to small r. And again we have to show that dy upon dx is equals to y by x, and given that where r is a constant function. If we have to prove dy upon dx is equals to y by x, then we first take given function sin of px raised to the power m minus qy raised to the power m upon px raised to the power m plus qy raised to the power m is equals to small r. If we take sin right side, then we can write as p into x raised to the power m minus q into y raised to the power m upon p into x raised to the power m plus q into y raised to the power m is equals to this sign convert into sin inverse of small r. Here r is constant function. Also we can write sin inverse r is also constant. Hence we can write sin inverse r is k. If we take this term right side, then we can write p into x raised to the power m minus q into y raised to the power m into p into x raised to the power m plus q into y raised to the power m. Now if we multiply this term k, p x raised to the power m, we can write p x raised to the power m plus k q y raised to the power m, p x raised to the power m minus q y raised to the power m. If we take x raised to the power term left side, then we can write p into x raised to the power m minus k into p x raised to the power m is equals to k q y raised to the power m, or q y raised to the power m, this minus converted to plus q y k q y raised to the power m q y raised to the power m. If we take x raised to the power m common here and y raised to the power common here, we can write p minus kp into x raised to the power m is equals to here kq plus q into y raised to the power m. If we take this term y raised to the power m left side, we can write it x raised to the power m upon y raised to the power m is equals to kq plus q upon p minus kp. Here again whole terms kq plus q p minus kp is a constant function, then we can write is x upon y whole raised to the power m is equals to kq plus q upon kp minus p. If we differentiate given function with respect to x, then we can write here by using the derivative of x raised to the power m into x upon y whole raised to the power m minus 1, and we can take again a derivative of x upon y. We know that kq plus q upon kp minus p is a constant function and the derivative of constant function is 0. Hence we can write it m into x upon y whole raised to the power m minus 1 is derivative of x upon y is equals to 0 into or 0 this term. If we take this term right side, then 0 into this term are 0. Therefore, we know that the derivative of x upon y, which is y into derivative of x minus x into derivative of y upon y square is equals to 0. If we shift this y square right side, then we can write 0 into y square is also 0. We can write y into derivative of x is 1 minus x into derivative of dy by dx is equals to 0 into y square is 0. If we shift this term x into dy by dx right side, then we can write x into dy by dx is equals to y. Now, if we shift x right side, x is multiple of dy by dx, then we can write dy upon dx is equals to y by x, which is a required proof of dy upon dx is equals to y by x. Hence proved. Hence proved. In next question number 4, given that if sec inverse of x cube plus y cube upon x cube minus y cube is equals to twice a, then we have to show that dy by dx is equals to x square tan square alpha upon y square. Here alpha a is constant. We can write here, given that sec inverse of x cube plus y cube upon x cube minus y cube is equals to twice a. We can write this term sec inverse converted into cos inverse. We can write also cos inverse of x cube minus y cube upon x cube plus y cube is equals to twice a. If we shift cos inverse right side, then we can write also it x cube minus y cube upon x cube plus y cube is equals to cos 2a. Now this x cube plus y cube multiple terms we write right side, then we can write x cube minus y cube is equals to cos twice a x cube plus y cube. Now if we multiply this bracket, we can write x cube cos 2a plus y cube cos 2a x cube minus y cube. We take the terms of x left side and terms of y right side, and we can write it x cube minus x cube into cos 2a y cube minus y cube, shift right side, then become positive, plus y cube cos 2a. If we take x cube common, then we can write 1 minus cos 2a x cube. If we take y cube common, 1 plus cos 2a into y cube. We know that 1 minus cos 2a is equals to sin square a into x cube. 1 plus cos 2a is equals to cos square a into y cube. This cos square a, if shift to its right side, then we can write sin square a x cube sin square a upon cos square a is equals to into x cube is equals to y cube. Now we have to prove dy upon dx is equals to x square tan square alpha upon y square. We can write it, therefore y cube is equals to sin upon cos tan square a x cube. Now if we differentiate given function with respect to x, then we can write the derivative of y is 3y square into dy by dx. Here tan square a is constant function and the derivative of x cube is 3x square. Now we have to prove only dy by dx. Then we can write dy upon dx is equals to 3x square tan square a upon 3y square. Here 3 cancel. Hence, we can write dy upon dx is equals to x square tan square alpha upon y square, which is the required derivative of a, which is required proof of dy by dx. Next question, which is question number 5. If y is equals to under root of tan x plus again under root of tan x plus again under root of tan x plus again under root of tan x up to and so on infinite under root of tan x. After that, we have to prove that dy by dx is equals to sec square x upon 2y minus 1. Now first, we take the given function y is equals to under root of tan of x plus again under root of tan of x plus again under root of tan of x plus which is infinite term. If we have to prove dy by dx is equals to sec square x upon 2y minus 1, first we take square both sides, squaring both sides. If we square both sides, then y square is equals to tan of x plus under root of tan x plus again under root of tan x plus under root of tan x plus and so on infinite terms. This term under root tan x plus under root tan x plus under root tan x as it is. Hence again we can write it y square is equals to tan x plus y. Now if we differentiate given function with respect to x, then we can write the derivative of y square is 2y into dy by dx. Here derivative of tan x is sec square x and the derivative of y, which is dy by dx. If we take this term dy by dx left side, then we can write 2y into dy by dx minus dy by dx is equals to sec square x. If we take dy by dx common, then we can write 2y minus 1 into dy by dx is equals to sec square x. Then we transfer this 2y minus 1 on the right side, then we can write sec square x upon 2y minus h, 2y minus 1, which is a required proof dy by dx is equal to sec square x upon 2y minus 1, hence proved. Again in last example, question number 6, given that if under root of 1 minus x square plus under root of y square, under root of 1 minus y square is equals to a into x minus y, then we have to show that dy upon dx is equals to under root of 1 minus y square upon 1 minus x square. First we take the given function, given that under root of 1 minus x square plus under root of 1 minus y square is equals to a in bracket x minus y. Now if we put x is equals to sin alpha and y is equals to sin beta, then we can write it under root of 1 minus sin square alpha plus under root of 1 minus sin square beta is equals to a in bracket sin alpha minus sin beta. 1 minus sin square alpha is cos square alpha plus 1 minus sin square beta is cos square beta is equals to a in bracket sin alpha minus sin beta. Here under root of cos square alpha is cos alpha plus cos square beta is cos beta is equals to a sin alpha minus sin beta. We know that sin a plus sin, we know that some of rules of trigonometric function, which is cos a plus cos b is equals to 2 cos of a plus b upon 2 into cos of a minus b upon 2, and sin a minus sin b is equals to 2 cos of a plus b upon 2 into sin of a minus b upon 2. By applying this rule, we can write this function cos alpha plus cos beta is 2 cos of alpha plus beta upon 2 into cos of alpha minus beta upon 2. Here a is as it is. Sin alpha minus sin beta, we can write it 2 cos of alpha plus beta upon 2 into sin of alpha minus beta upon 2. Here we can write again twice a cos of alpha plus beta upon 2 into sin of alpha minus beta upon 2. Right side as it is 2 cos of alpha plus beta upon 2 into cos of alpha minus beta upon 2. Here 2 cancel. Cos of alpha plus beta upon 2. Cos of alpha plus beta upon 2. We can write it cos of alpha minus beta upon 2 is equals to sin of alpha minus beta upon 2. But we have to prove that dy upon dx is equals to under root of 1 minus y square upon 1 minus x square. Here cos of alpha minus beta 2 upon 2 is equals to sin of alpha minus beta upon 2. If we take this sin of alpha minus beta upon 2 right side, left side, then we can write cos of alpha minus beta upon 2 upon sin of alpha minus beta upon 2 is equals to a. Cos upon sin is cot. Similarly, we can write is cot of alpha minus beta upon 2 is equals to a. If we shift this cot right side, then we can write alpha minus beta upon 2 is equals to cot inverse of a. If we shift again to right side, then we can write alpha minus beta is equals to 2 cot inverse of a. We know that the value of alpha is equals to sin inverse x and beta is equals to sin inverse y. Hence we can write sin inverse x minus sin inverse y is equals to 2 cot inverse of a. If we differentiate a given function with respect to x, then we can write the derivative of sin inverse x minus derivative of sin inverse y is equals to 2 cot inverse x. Derivative of sin inverse x is 1 upon under root of 1 minus x square. Derivative of sin inverse y is 1 upon under root of 1 minus y square into dy by dx. And the right side 2 cot inverse a, which is constant function, we know that derivative of constant function is 0. If we shift this term right side, then we can write 1 upon under root of 1 minus y square into dy upon dx is equals to 1 upon under root of 1 minus x square. Implying that we can write dy upon dx is equals to under root of 1 minus y square upon 1 minus x square, which is the required derivative, or dy upon dx is equals to 1 minus y square upon 1 minus x square. Hence proved.